Okay, a kinematic example. A jackalope, you should look up jackalopes, see what you know about them, travels west, accelerating from 0 to 10 meters per second in 5 seconds. Let's say 10 meters per second is its top speed. It is then assailed by a predator. Do jackalopes have predators? And makes a quick turn going east at its top speed for 10 seconds. Don't worry about how it makes that turn. How far has the jackalope gone from where he or she or they started? So, how do we solve this problem? Well, we always start a problem by doing what first? We draw a picture. So now we know that the jackalope travels west, so let's choose west. Typically we don't have to, but west could be to the right, to the left, up or down, but let's just choose our typical direction for west, and let's make west in this direction. So the jackalope, I'll just draw a spherical jackalope, assume a spherical jackalope, and let's just say, let's say that the jackalope goes in that direction, starts at 0, having a little iPad trouble. Okay, so try again. So let's say that this is something of a picture, starts from an initial velocity of 0 to a final velocity of 10 meters per second, it takes 5 seconds. So I've indicated that somehow on a diagram. But then the jackalope, so we really need a second picture for the second part. The jackalope is going 10 meters per second in the opposite direction, 10 meters per second. I don't know whether to call that an initial or a final, for 10 seconds. So it ends up somewhere else, I don't know where. So it ends up going for t equals 10 seconds. I didn't say it slows down. Oh, actually what I meant to say, it going east at its top speed constantly. It's going at a constant speed for the second part of the trip. Constantly at its top speed for 10 seconds. So its final velocity is at the end of the second part of the trip is 10 meters per second. So the first key here is to recognize, is this a constant acceleration problem? And the answer is no, it's not a constant acceleration. The jackalope has a different acceleration for the first part of the trip from when it's going west from the second part of the trip when it's going east. It's got a different acceleration, not because it's turned around. That doesn't change its acceleration. It changes acceleration because it's changed the rate of change of speed. Changed the rate of change of velocity. Changed the rate of change of velocity. In the second part of the trip, it's going at constant velocity. Actually, what is the jackalope's acceleration for the second part of the trip? The jackalope's acceleration for the second part of the trip, because it's going at constant velocity, we know that the acceleration for this part of the trip is 0. The acceleration for the first part of the trip, I guess I'll just call that A1, is unknown. That's not what we're looking for. But we don't know it. Whereas the acceleration on the second part of the trip, because going at constant velocity, A2, is 0. So the point here, the reason why I've written down the accelerations in the pictures, is to point out that this is not a constant acceleration problem. So what do you do with constant acceleration problems? We discussed that you must break them up into constant acceleration pieces, which is why I drew two separate pictures. Two separate pictures where we have constant acceleration in each. So we've got to treat each piece separately, and so I'll actually even put a dividing line here. Treat each piece separately and then add them up. So let's see, what are we going to do? So let's just do the first part first. Let's do the first piece. We'll call it 1, and the second piece is 2. We'll do 1 first. So in part 1, what color should I write in? I'm going to choose green. Let's identify our variables. V, V0, A, T, delta X. What do we know and what don't we know? Well, we know the final velocity is 10 meters per second. And actually, before I even get any further, we're going to do one other thing so that I don't have to go back and think about the signs. Let's choose our positive direction. And since we're going west to begin with, let's just choose that as our positive direction. Let's make this the plus x direction. We'll make to the left the plus x direction. There's nothing magic about right being plus x. We can choose whatever direction we want as being plus x. So since that's the plus x direction, and the final velocity is pointing in the west direction, then the velocity here is plus 10 meters per second. The initial velocity is 0. The acceleration is unknown. The time is given as 5 seconds. It is plus 5 seconds, but we don't normally treat time as a vector. And delta x, that's what we want to know, is how far has Jack gone? Delta x is an unknown. So that's for the first part. We'll come back to this second part later. Let's just finish the first part. So how far has Jack gone in the first part? In the first part, we can go ahead and use our kinematic equations and solve for delta x. We can write down our 3 kinematic equations and look at our 3 kinematic equations and say, I want to know delta x. I have a delta x in the first equation, I have a delta x in the third equation, so maybe one of those equations is the best one to use. And I don't know acceleration. Let me just go through the equations. I don't know the acceleration. I do know the time. I do know the time. Check. I do know, sorry, I'm pausing. I do know V0. I do know time. Oh, okay. So the first equation, no, I don't know acceleration. Okay, right. So now I look at the third equation. Velocity, I know velocity. I know initial velocity. I don't know acceleration. But I'm looking for delta x, so in both of those equations I have an unknown. So I'm going to have to, I can't use either of those equations, or even those 2 equations together to solve for delta x. I'm going to have to use the second equation as well. I know velocity, I know v0, and I know time. The second equation is going to give me a, and then I can go ahead and use that in the first or third equation to get x. So, again, I'm still only solving for the first part of this problem. And I'm going to say, I got to use the second equation. V equals V, so I'm going to use that. V plus 10 meters per second equals V0, 0, plus A times T, which is 5 seconds. So therefore, A is equal to 2 meters per second squared. I can then go ahead and plug that into either the first or the third equation. I'm going to go ahead and plug that into the third equation and solve for delta x. So I can say v squared, which is plus 10 meters per second squared, equals v0 squared, 0 squared, plus 2a. A is now plus 2 meters per second squared. I didn't make a big deal about that, but that was a positive number. That was positive. Times delta x. So I can go ahead and solve that equation for delta x, and I get plus 25 meters. Do the math, right? Square the 10 meters per second squared, and then divide it by 4 meters per second squared. All those numbers are positive, so we end up with, 10 meters per second quantity squared gives me 10 meters squared per second squared, divided by 4 meters per second squared, and we're left with 25 meters. So, for the first part of the problem, the jackalope goes 25 meters. It's plus 25 meters because we chose the positive direction to be west, and the jackalope's going west, so that makes sense. Plus 25 meters in the west direction. Just to be clear, now this is something we really need to get into the habit of doing. I'm going to plug this right here and say, hey, from now on, we really need to, instead of just saying plus or minus, we want to say what direction. In this case, the positive direction is west, so plus west. Or if it was x, I would say plus x, etc. You'll see. We'll start doing that a lot more. In any case, what about the second part? The second part, the jackalope is going 10 meters per second east for 10 seconds. And actually, you can probably do that in your head and see that it must go 100 meters east. And so that it is actually plus 100 meters east, which is also equal to minus 100 meters west, right? Because the displacement is to the right. Or if you think of this as the x and the y direction, right, it's going 100 meters to the right, which is the minus direction, so it's going minus 100 meters. And what I wasn't careful about is plugging into the equations. Let's go ahead and if you didn't see that as being a minus 100 meters west, let's just go ahead and do that like a kinematic problem. Okay, so here's part B of the jackalope problem. And what I want to point out is the steps that I've taken. Step 1, draw a picture. Step 2, choose the positive direction. That's in the box. Step 3, write out all of my variables. Now here we got to be careful. We've got negative variables because V and V0, those arrows, point in the opposite direction of my plus x direction. Then I have negative quantities. So the negative in the picture is given by the arrow. The negative is given by the arrow. When I put that in numbers, the negative is given by a sign. Okay? So I've got to have the negative signs in front of those values. Delta x is what we're looking for. V final and V initial are both minus 10 meters per second because it's constant velocity. Acceleration is 0. And we're given t is 10 seconds. I put a positive sign just to make sure we know it's positive 10 seconds. Then I write down my kinematic equations. And I say, ooh, I need to solve for delta x. So I can solve for delta x either from the first equation or the third equation. And I will use the one that is most useful, which is the first equation. The one that's going to give me an answer that is useful. You could try the third equation and you will see why it is not so useful. And so I get delta x is 1/2 a t squared plus v0, and we have to carry our signs, times t, and so what I end up getting is minus 100 meters. That's minus 100 meters in the x direction, or the x direction is the west direction, minus 100 meters west, or 100, which is the same as plus 100 meters east, just as a matter of interest, but that's not important here. So what's the final answer to the question that was asked? The question that was asked is, how far has Jack gone from where he or she or they started? And the answer is Jack has gone a total, delta x total equals delta x part 1 plus delta x part 2. I guess I called it A and B. Eventually I changed my 1s and 2s to A's and B's. And delta x part 1 was 25 meters west plus 25 meters west minus 100 meters west is equal to minus 75 meters west, or, which is fine, which is also equal to plus 75 meters east. Jack has gone 75 meters east of where he started, he or she. I'm calling him Jack because he's a jackalope. I don't actually know what his gender is.